Hello, my name is Kayne Putman and I'm the Regional Vice President for our team of applied AI experts across Europe. DataRobot offers a pure-play enterprise AI platform to organizations who are looking to accelerate their team of data scientists or are seeking to democratize data science. We have developed our platform's breadth and depth of capabilities for over 10 years, and because DataRobot is a plug-and-play platform and any organization has machine learning use cases, we support customers across any industry vertical in a joint mission towards value-driven AI. So for today's purpose, let's pretend we're a team of data scientists who work for a European government body, and we want to understand the risk factors associated with flooding for various cities across Europe. This is a subject area close to my heart, having personally suffered the consequences of flooding back in 2014. Now, of course, with data science, everything starts with data, and we've sourced a wide data set from OECD with many variables around climate, the economy, demographics, and so on, and we can easily download this and bring this straight into DataRobot. Our target variable will be the share of population exposed to river flooding within a 100-year return period. But interestingly, the value of this variable only exists for 2015, and because this dataset has a temporal aspect to it, we will set this up using automated feature discovery to learn from other features over time without having to write any SQL. From our primary dataset, we will kick off a new DataRobot project where there will be an exploratory data analysis instantly performed. Where down here I can see summary statistics of the variables in our dataset. And DataRobot is great at handling varied data types. So when I loaded this dataset containing latitude and longitude, it automatically created this geospatial feature, which is awesome as it allows me to explore variables across a map. And unsurprisingly, we see the Netherlands with the highest risk of river flooding across Europe. What I will do now is choose our target variable, and then join on the dataset I saw a second ago to benefit from automated feature engineering. DataRobot has automatically detected the IDs to join the datasets upon, and I will configure a number of different time windows to build a richer feature set. Now we simply click the Start button to kick off the process of discovering and building new features. This stage usually takes a couple of minutes, so let's zoom ahead. Here is our list of newly built features, and finally we can go in and understand how every feature has been built through our feature lineage views. Now we are ready to train models. Now we have our feature set, we want to train some models to learn which are the most impactful risk factors for river flooding. The no free lunch theorem in machine learning states that no single algorithm performs best for every problem. So DataRobot automatically selects a bunch of blueprints to be trained, including open source and DataRobot approaches, where they will be ranked on this leaderboard on accuracy. And this means that I can leverage the latest and greatest without the need to know how to code. Let's move ahead to a completed project. Our group will likely want to understand our best blueprint in more detail, so let's pick this random forest model. Firstly, we would want to understand what is actually happening. And here we can see this blueprint including the modeling algorithm, but also all the necessary pre-processing steps for that algorithm to perform well. And whilst I'm purely interested in speed today, my fellow data scientists may want to iterate on this further, which they absolutely can. They could edit this blueprint or even bring in their own custom code. Next, I want to understand accuracy in more detail, and I can do that in a couple of ways. One way is to look at a lift chart. Since this is a regression problem, we could also look at our residuals. And we can also inspect accuracy over space to understand which cities or which countries our model might be over or under predicting in. We see some cities underperforming, which we could now break out and model separately to try and increase overall accuracy. And this is exactly the benefit of an AutoML approach. Instead of having just one model, we could rapidly experiment and develop a suite of models, all using state-of-the-art approaches and data science guardrails, and that allows data science and non-data science teams to collaborate. But often the problem with data science isn't the modeling, rather communicating it with non-technical stakeholders. So let's explore some strategies of how DataRobot allows us to do this. Firstly, I want to understand the most important risk factors. And here we can see our most important feature is a variable which was derived from heating degree days. And as we can see here, the higher this variable is, the higher the chance of river flooding. Now these are global ways of assessing our feature impact, but we might also want to inspect this at an individual prediction level. And prediction explanations allows us to do exactly that. To satisfy regulators and internal risk teams, next I might want to build some documentation of our modelling approach coupled with these insights, and DataRobot does this for us in one click. Finally, we can supercharge our interactions with our business stakeholders by allowing them to interact with the model through enterprise applications. Here we have built a what-if app, where anyone can enter some input values and get a prediction using this trained model. This facilitates business stakeholders to engage with data-driven scenario planning. Our model is now ready to be deployed, so let's dive into ML production. Prior to DataRobot, our models fell into a chasm at this point, as there was no easy way for us data scientists to collaborate with our engineering, IT ops, and risk teams to ensure our models could be integrated into business-critical applications and processes. There are a number of ways a model can be deployed in DataRobot, but today I'll choose to deploy this model to a dedicated REST API endpoint. Once we have configured our deployment settings, we'll need to integrate it with our data pipeline to make predictions on an ongoing basis. If we wanted to integrate this model with a front-end system or web application, we could use this production-ready API code, or we can configure a job definition to integrate into some well-known databases. This will be added to our deployment homepage, which offers us a single pane of glass for managing all of our models, no matter where they are built or deployed. For example, here I have a model originally built in Python. This means that our team can continue to leverage external modeling and experimentation tracking tools whilst benefiting from DataRobot's governance and DevOps best practices for model deployment. Personally, I really like MLflow, so my training parameters, accuracy metric scores, and other artifacts could easily be brought into DataRobot to use in an automated compliance document, and generally to centralize our model metadata across different building scenarios. Moving on to model monitoring, DataRobot tracks whether a model is fit for purpose in three ways: service health, data drift, and accuracy. Let's dive into one of these use cases. Service health gives us an IT lens on how this deployment is working operationally. It offers views like latency and data and system errors. Data drift helps us understand whether our dataset that we're scoring today has changed significantly since when we trained our model. The x-axis is feature importance, and the y-axis is a drift metric called population stability index. So the worst case scenario is a feature was very important, but it has drifted lots. Lastly, we can inspect model accuracy over time to see if our model has degraded significantly or not. Notifications can be configured for each deployment to alert us to when a model is showing potential problems, so we can triage what we might need to do next. And this is where DataRobot's rich model management functionality can also help us. Things like champion-challenger frameworks, where competing approaches can be inspected over time to see if they would perform better if they were in production instead. DataRobot can also automatically optimize the performance of our models through retraining policies. We have two set up for this deployment, one which is time-based, which reruns AutoPilot every month on new training data and replaces the existing champion model, and one which replaces the champion model when it sees that our drift metric has gone beyond a particular threshold. We have developed a number of assets over the course of our investigation, including datasets, projects, deployments, and apps. To organize all our ML assets across a use case into a single place, DataRobot has built a new workbench where all personas can collaborate. We saw how a business user can interact with a model during the experimentation phase, but it is also important they are able to interact with the model once deployed. So continuing the collaboration with the business, I have built another app on top of the deployment we made earlier with various model insights. Furthermore, these can now be fully contextualized thanks to our integration with OpenAI. We see here, for example, that another important feature is a city's exposure to very strong heat stress. As a data scientist, I might want to continue my research into this. So through DataRobot notebooks, thanks to again our integration with OpenAI, I can rapidly build some boilerplate code to explore this. Firstly, I want to access my datasets in AI Catalog. And then I want to plot this feature against a good base map. Finally, we all know projects are never this easy in reality. We have likely found some data quality issues through our investigation, so I might need to go back to the source data and apply further data preparation steps prior to modelling. Through DataRobot's data preparation capabilities, we can quickly build up a recipe. Multiple operations can be carried out here, like computing new values, filtering, and so on. Furthermore, if this data is stored in Snowflake, for example, this recipe can be pushed down for processing, only bringing back the final dataset, meaning I can leverage the security and governance of our data warehouse. That's it for the demo. Now let me wrap up with a quick summary of what we found. Through these quick demos, we've seen how we could ingest raw data and perform automated feature discovery, how we could invoke a model competition and engage business stakeholders with model insights, how we could easily deploy that model and observe some of the model monitoring and management capabilities. And finally, we saw how business stakeholders and data scientists could go deeper, guided by DataRobot's integration with OpenAI through applications and notebooks, and how analysts can continue to iterate on datasets through our data preparation capabilities on DataRobot's new workbench. Through this research, we have found a number of interesting insights about what drives river flooding, including heating degree days, PM2 exposure, and strong heat stress days. Furthermore, through feature discovery, we were able to build some rate of change variables, which also proved very predictive. Finally, surprising to us, but very few features across the economy and transportation categories, for example, did not offer much signal. But we suspect that's probably because they prove redundant when climate and air pollution variables are already included. Thank you for watching, and I hope this was useful.